In this video, we will be talking about temperature and energy transfer. Specifically, we will be working on temperature conversion, so converting between Celsius, Fahrenheit, and Kelvin. And in terms of energy transfer, we're going to be talking about specific heat and working with the formula Q equals mc delta T. First up, we're given three different formulas. The one you want to use depends on where you're trying to go. The first formula we have here is the Fahrenheit formula. So this Fahrenheit formula is going to allow us to convert, or find Fahrenheit if we're given Celsius. And when I have this T sub F here, so this T sub F, that just means the temperature in Fahrenheit. T sub C means temperature in Celsius, and then T sub K means temperature in Kelvin. So again, this first formula, this is going to be used when we want to convert Celsius into Fahrenheit. Second one is Fahrenheit into Celsius. And then the last one is Celsius into Kelvin or Kelvin into Celsius. Notice that we do not have a formula to go straight from Fahrenheit to Kelvin. Okay, there is no formula straight from Fahrenheit to Kelvin. Now we could derive one, but simply you just have to work through. We're going to have to use multiple formulas in that. The highest atmospheric temperature ever recorded on Earth was 57.8 degrees Celsius. Express temperatures in degrees Fahrenheit and Kelvin. In terms of this one, this is actually going to get it to where we're going to have to use all three formulas. To start off, I'm going to go ahead and convert Celsius to Fahrenheit. So I'm going to choose a color for that. Degrees Celsius to degrees Fahrenheit. So I'm given Celsius, and I have to find Fahrenheit. For this, I'm going to use this top formula. Now, inside of these formulas, if you've taken some other class or had to do some other conversions, you may have been using the fraction 9/5 instead of 1.8. That's fine. They're the same thing. And so the little discrepancy between, some of the far out decimals really isn't going to make a difference in terms of these calculations. So we are going to take temperature Fahrenheit, which is what we're solving for, equals 1.8 times the temperature in Celsius plus 32 degrees. We plug in what we're given, so it's going to be 1.8 times 57.8 plus 32. Therefore, our temperature in Fahrenheit is going to equal about 136.04 degrees Fahrenheit. The next thing that it asks us is to calculate Celsius into Kelvin. So next place we're going to go, degrees Celsius to degrees Kelvin. I need to use this bottom equation right here. I'm trying to find Kelvin. In terms of the formula, that's going to be temperature Kelvin equals Tc plus 273. And again, some use 273.15. Honestly, it's not going to make that big of a difference. We're dealing with large numbers here. And also for the purpose of this class, using 273.15 just isn't, we're fine without it. Plug in what I'm given, so that's 57.8 plus 273, which brings us to 330.8 Kelvin. The last thing that I want to do is I want to go ahead and introduce one to where you have to use both, because it is really realistic to expect you to do so. Say I'm given Fahrenheit. So say I'm given 50 degrees Fahrenheit, and I want you to calculate to Kelvin. Remember on the last slide I said we have no direct formula to say, okay, Fahrenheit to Kelvin. What we actually have to do is use a combination of both. What I first asked myself is, okay, Kelvin, which formula do I have to use to calculate Kelvin? And that's going to be this bottom formula. I have to use that to get to Kelvin. That's the only one I have. Well, what do I need to solve for that? The first thing I need is I need temperature in Celsius. I have to have that. And then the next thing that I need is that 273, which is already given. So we have to convert from Fahrenheit to Celsius first, because I really need this temperature Celsius to solve this problem. So temperature Celsius equals the temperature Fahrenheit minus 32 divided by 1.8, and that's this formula right here. When I plug in my numbers, 50 minus 32 divided by 1.8, make sure you're careful in your calculator about order of operations here. So I would put this in parentheses in your calculator just to be safe. This is going to equal 10 degrees Celsius. The next thing I need to do now that I know Celsius is I can finally use this formula right here. So temperature Kelvin equals temperature Celsius plus 273. This is just going to be 10 plus 273, and that gives me 283 Kelvin. Also notice that I'm not writing degrees Kelvin or saying degrees Kelvin. That's wrong. It's just Kelvin, whereas Fahrenheit is degrees and Celsius is also degrees. Next, we're going to be talking about specific heat and what it means when things have higher or lower specific heat. So it just describes how much energy is required to raise an object's temperature. And that's very scientifically defined as the quantity of heat required to raise a unit of mass of a given homogeneous material 1 degree Kelvin or 1 degree Celsius in a specified way given constant pressure and volume. This is what specific temperature really means. Say, for instance, we have water down here. All right, so I'm looking at water. In terms of water, it has the highest specific heat out of everything. Whereas if we look at something like iron, iron has a much lower specific heat than water. This means that water has the capacity to hold more heat than iron. You can think about this conceptually. If you have, if you want to cook something on the stove, right? You typically would use an iron skillet. Why would you use an iron skillet? That's because it allows heat to pass through it. If heat passes through something, it means it doesn't hold the heat in well. Whereas water is really good about holding heat in well. That's why it takes so long for a pot of water to boil. Also, if you're thinking about going to the swimming pool or going to the beach, the first day that we have 90-degree weather, you just don't go jump in the pool if we've had a series of, let's say, 60-degree weather. That's because it's going to take that pool or the beach, the temperature of that water, a longer time to rise. So you usually wait about a week of, 80 or 90-degree temperature before you go jump in the pool. Of course, that is unless you like freezing cold pool. So again, if you have a low specific heat, heat is going to pass through very easily, whereas if you have a high specific heat, it's going to be able to hold it in easier. In terms of specific heat equation calculations, we have Q equals mc delta T. This is where Q is energy expressed in joules. C is the specific heat constant, which can have varying units depending on what your other values are. So it can be those units right there. M is mass, and mass can be in kilograms or grams, again, depending on other units in the problem. And then we have delta T, which is the change in temperature. And that can be in Kelvin or degrees Celsius. Let's put a little degree symbol there, degrees Celsius. Looking at our first specific heat calculations, how much energy will cause 7 kilograms of iron to increase its temperature by 25 Kelvin? The specific heat of iron is 449 joules kilograms times Kelvin. Solving this problem out, Q, M, C, delta T. It's asking for energy, so energy is abbreviated by Q. The mass, it gives us 7 kilograms. A temperature change of 25 degrees Kelvin, or excuse me, 25 Kelvin. The specific heat of iron is 400, oops, why is this not, it keeps erasing. 449 joules kilogram times Kelvin. When you're solving these problems, because things like mass and the specific heat constant and temperature can have different units, as long as our units are canceling or as long as our units are the same, we don't have to worry about unit conversion. So for this problem, we're given Kelvin as temperature and Kelvin in the specific heat capacity. We're given kilograms as a mass, and we're given kilograms as the unit in specific heat capacity. So we don't need to worry about changing any of these units. We should be able to use them as they are. So Q equals mc delta T. Our mass is going to be 7 kilograms. And we have 449 joules, kilograms times Kelvin, and then lastly we have 25 Kelvin. Now, one thing that I urge you to do when you're solving these problems is make sure you're writing out all your units, because this is where you're going to catch yourself in case you need a unit convert. So we have kilograms over kilograms, that cancels out. We have Kelvin over Kelvin, that cancels out. And this leaves us in units of joules, which is exactly what we want because we're solving for energy. If we put this in our calculator, it's going to give us a value of 78,575 joules. For our next problem, water has a specific heat constant of 4,186 joules grams times Kelvin. It is heated using 8,240 joules of energy. If the temperature changes from 50 to 75 degrees Fahrenheit, what is the mass of the water? All right, so I had a little technical difficulty on the last slide, so it kind of looks like the top part's erased, but if you just rewind the video, the top part calculation will still be there. Back to our problem. So I already read it out to you. So we are going to line up the variables. We're asking, it says, what is the mass of the water? So that's going to get the question mark. It gives us a specific heat capacity constant, 4,186 joules grams Kelvin. We're giving a energy value, 8,240 joules. And lastly, we're given a temperature change of 50 degrees Fahrenheit to 75 degrees Fahrenheit. Now we have to make sure all of our units are the same, and currently they're not. Currently we're given Fahrenheit and Kelvin. We're going to have to change one of those. I highly recommend never changing the specific heat constant. It's going to be too much of a headache. So what we need to do is to change Fahrenheit to Kelvin. Now this is very important. When we find the change in temperature, how we find the change in temperature is the change in temperature is defined as the final temperature minus the initial temperature. You need to wait until it's in the appropriate units to use this formula, the one in purple. If you say 75 minus 50 degrees and get 25 degrees Fahrenheit and change that to Kelvin, that will be wrong. Okay? You need to convert these first and then find the change in temperature. And we can see that here in a few minutes. So for instance, again, I'll just write it down here. If we went ahead and solved this and said 75 minus 50 degrees, and we get 25 degrees Fahrenheit. If we were to change that into Kelvin, the Kelvin value, so 25 degrees Fahrenheit into Kelvin, I'm not going to do the math on this, but it gives you a value somewhere around 269 Kelvin. Now, let's convert it first and then use the formula, and you can see how we won't come up with 269 Kelvin. It's going to be different. So I guess it's actually fortunate that I kind of messed up on the previous slide, so I have extra room up here. So I'm going to take this 50 degrees Fahrenheit to Kelvin up here. Now, the formula we're going to have to use for that, remember, we're going to have to use two different formulas. So we have temperature in Celsius is going to be 50 minus 32 divided by 1.8, which gives us 10 degrees Celsius. If we want to convert that to Kelvin, it is going to be 10 degrees Celsius plus 273 Kelvin. That's going to give us 283 Kelvin. So 50 degrees Fahrenheit to Kelvin gives us 283 Kelvin. Let me kind of erase that. Looks like a little decimal there. Clean some of this up here. So 283 Kelvin. So instead of using 50 degrees down here, we now have 283 Kelvin. Let's do the same thing, but using 75 degrees Fahrenheit. So I'm not going to do the calculation again because it's right up top and we did it on the previous slide. This would give us 297 Kelvin. So that's what we're going to use down here, 297 Kelvin. Now let's plug in those two numbers to find the actual change in temperature. We're going to have the final temperature, which is going to be 297 minus 283 Kelvin. That's going to give us a value of about 14 Kelvin. Now look, I told you from the beginning, if you did Fahrenheit or subtracted the two values, found the change in, and then converted it to Kelvin, you get 269. But in actuality, we've only increased 14 Kelvin. So make sure you convert, then find the change in temperature. So now that we have the temperature that we're going to use, we can actually solve this equation. Q equals mc delta T. We're trying to solve for mass, so we need to get that on a side by itself. That is going to be mass equals Q divided by C delta T. Q is going to be 8,240 joules. Again, make sure you're writing your units so you can see what cancels out. Then C, ooh, well, this thing is being ornery today. 4,186 joules, grams, times Kelvin. And lastly, put our change in temperature there, which is 14 Kelvin. In terms of unit cancellation, Kelvin cancels out with Kelvin, joules cancels out with joules, and that is going to leave us in units of grams. So mass is going to equal 0. Alright guys, so PowerPoint just crashed on me again. I really don't want to go back and record that whole thing. We were on the last step. So the answer for the previous slide came out to be 0.141 grams. So that was the answer for the previous slide. We were almost there, so I didn't want to go back and have to redo that whole thing. But that is the answer for the last slide. Let's look at this specific heat calculation. A 3.5 kilogram piece of iron absorbs 23,719 joules of energy. If the iron has a temperature of 295 Kelvin before it absorbs the energy, what will be the final temperature of the iron after it absorbs the energy? The specific heat of iron is 449 joules divided by Kelvin times kilogram. One formula I want to go ahead and write up top just so we remember it. I'll write it in blue here. Is that the change in temperature, this variable of the formula is defined by temperature final minus temperature initial. Here it's asking us to solve for the final temperature. This is kind of a multi-step problem. So in terms to solve for the final temperature, we're going to need to use this equation right here. I am going to write down all the variables. Now, let's see what it gives us. Temperature final gives us the question mark. That's what it's looking for. The change in temperature, we are unsure of at the moment. And the initial temperature, it tells us right here in the problem. The iron has a temperature of 295 Kelvin before it absorbs the energy. 295 Kelvin is going to be our initial temperature. There we go. In order to solve this problem, we also have to know this change in temperature variable. We have to know this change in temperature variable. You have to ask yourself, well, given all of the information, how can I calculate this change in temperature? And the answer to that is we're going to be using this QC, or Q equals MC delta T. We're given a Q, we're given an M, and we're given a C. We can rearrange and solve for delta T. So let me do that down here at the bottom. Erase it. Q, M, C, and delta T. Our mass is 3.5 kilograms. We're trying to solve for the change in temperature. Our constant is 449 joules divided by kilograms times Kelvin. And the amount of energy we're putting into this is 23,719 joules. If we rearrange this formula and solve for delta T, it's going to give us Q divided by MC. All of our units are matching each other, so we can solve this formula as is. We don't need to do any unit converting here. Divided by 3.5 kilograms. Again, always make sure you're writing down your units, guys. That's how you catch yourself. Times Kelvin. In terms of our units, Kelvin, Kelvin is actually going to be our unit left by itself because we're solving for temperature. Kilogram cancels out with kilogram, joules cancels out with joules. This is going to give us a change in temperature value of 15.09 Kelvin. What we're going to do is we're going to take this change in temperature value and we're going to plug it in right here. So I'm going to bring this 15.09 up here. Now that I have these two variables, I can solve for the final temperature. So delta T equals TF minus TI. We want to get temperature final on a side by itself. So we're going to add temperature initial to both sides. That will cancel out. So remember, since you're subtracting, you have to add initial temperature to both sides. That's going to cancel out. So it's going to be temperature final equals the change in temperature plus temperature initial. The change in is 15.09 Kelvin plus the initial is 295 Kelvin. This is going to give us a final temperature of 310 Kelvin. So that is going to be our final answer. The last thing I want to talk about today is what we call a heating curve. When we add heat to something, it's going to raise the object's temperature or it's going to change the object's state. And so we need to talk about what happens with a substance temperature while it's melting or boiling. Here is a classic example. We use something like water, typically always when you see these. We're going to start out down here at freezing. So we have an ice cube. It's of course frozen. We are going to start to add heat to this ice cube. As we do, the temperature is going to increase. So when we have these slopes, we're experiencing change in temperature. And we can say that for all of these slopes. Change in temperature, change in temperature. Down here, we're going to have this as a solid, and then a liquid, and lastly, as a gas. So those are also going to be the states on these little inclines right here. They're experiencing kinetic energy during this, okay? However, when you get to what I call these plateaus, so these flat parts, I guess yellow or green doesn't really stand out. Let me change to yellow. When we get to these flat parts right here, what is actually happening? We're still adding heat. The question is, why isn't the temperature rising? We're still adding heat, yet these plateaus say the temperature is not rising. That's because what's happening at this is that the temperature is going into potential energy. So potential energy is where it's being stored right here. Also, we're experiencing state changes here. So back to our definition up at the top, it says heat can raise an object's temperature or change the object's state. So if we're not raising the temperature, we're changing the object's state. So during these plateaus, we're experiencing state changes. For example, this bottom plateau, we're going from a solid to a liquid. And this next plateau, we are going from a liquid to a gas. So we have kinetic energy and temperature changes on our incline. We're in one specific state. On our plateaus, we're experiencing a rise in potential energy where we kind of have this equilibrium of two states. And that is going to be basically all that you need to know in terms of this heating curve. That should help you with the remainder of your notes. As always, if you have any questions, please let me know. Email me. I am here to help.